Here's an object, whatever it is. Maybe it's a car driving in a circle. Maybe it's a ladybug sitting on a record player. But this object has an angular velocity, omega. And in this case, that is counterclockwise, so this value of omega would be positive. There's another way I can describe its motion besides just talking about the angular velocity. So let's consider if I had a clock and I have two bugs. So in this case, I have a ladybug sitting closer to the center of this minutes hand, and I have a beetle sitting out here at the edge, still sitting on the same minutes hand. Now both of these bugs are going to have the same exact angular velocity, right? The angular velocity of each one of these bugs would be 1 revolution per hour, right? Because it's going to take them an hour if they're just sitting there on that hand on the clock. It's going to take 1 hour for that hand to make 1 full revolution. So both ladybugs have an angular velocity of 1 revolution per hour, and I could, if I wanted to, convert that 1 revolution per hour into radians per second. But something else is happening as these bugs are moving. So they're not walking, they're just sitting on that hand and riding the hand as it moves. The thing that happens is that the beetle is moving faster. Even though they have the same angular velocity, they're still both going to make 1 revolution per hour. The beetle is moving faster because look at the distance he has to travel. He has to travel a circle that has a circumference that's this big in 1 hour. And the ladybug only has to travel a circle with a circumference that's this big in that 1 hour. So somehow I want to be able to say, yes, they have the same angular velocity, omega, but I want to also be able to describe the fact that the beetle is moving faster. So the thing that's bigger for the beetle is what we're going to call tangential velocity. So in this case, we can always look at each moment that the object that's moving in a circle, which is represented by this angular velocity, omega, also is moving in the direction that's tangent to the circle. And I can call that a tangential velocity, and I can measure this value in meters per second. That's just like how fast is it going? How many meters per second is it traveling at? And we can relate the two. So the tangential velocity, well, this is our tangential velocity, omega is our angular velocity, and r is the radius. Okay, so this equation here relates the tangential velocity, how fast the object is actually going, to the angular velocity, which is how fast it's completing its circle, times the radius. So for the case of the ladybug and the beetle, they both have the same value of omega, but r is smaller for the ladybug because the circle that the ladybug is making is this small circle. So r is small for the ladybug, which means the tangential velocity of the ladybug is going to be small. For the beetle, r would be the distance from the beetle to the center. That's the radius of the circle that the beetle is making. R is bigger for the beetle, so the tangential velocity will be bigger for the beetle. Okay, he has to move faster so that he can get all the way around by the time he comes back here, whereas the ladybug only has to travel this little distance in that same amount of time. So it's tricky to keep these separate, but I want you to picture the beetle and the ladybug either sitting on a second hand, or minute hand like this, or maybe sitting on a record that's spinning on a record player. That's another way to picture it. And here's just kind of helps you kind of make sense of the difference between these two. The angular velocity, which we call omega, is measured in radians per second, and that is describing how fast the object is making a circle. How fast is it completing the circle? And these two are completing a circle in the same amount of time. So their angular velocities are the same. The tangential velocity is measured in meters per second, good old meters per second. That's what we're used to talking about. And that is simply measuring how fast the object is moving. So if you're imagining a car driving in a circle, the tangential velocity is what the car's speedometer would read. Like if your speedometer reads 30 miles per hour and you're in cruise control going 30 miles per hour as you make this circle, that's your tangential velocity. Your tangential velocity is 30 miles per hour. Normally we use in measurements of meters per second. Okay. So again, we could, if we know the period, how long it takes to go around here once, I could find the tangential velocity by taking this entire distance, 2 pi r, divided by that period, big T, and that would give me my tangential speed, because that's telling me how many meters, 2 pi r meters, in how many seconds, big T seconds, that's my period. And that would be my tangential velocity in meters per second. Okay, so here's 3 ladybugs. They're on a wheel. The wheel is rotating at a constant speed. I want you to rank from the smallest to the largest the angular velocities of these ladybugs. Okay, so think about it. How are their angular velocities related? Remember, angular velocity describes how quickly they are completing a circle. So think about that. Press pause. Think about it for a little bit. Well, in this case, they are all, because they're all on this disk, they all have the exact same angular velocity. They're all completing a circle in the same amount of time. Now, what's different about them is their tangential velocities. One of these ladybugs is going faster than the other ones. And the one that's going faster is C. C has to make a circle that's this big, this big, in the same amount of time that A and B have to make a circle that's this big. So A and B have the same radius of the circle they're making, so their tangential velocities are going to be the same. Whereas C, the circle that C is making is a bigger radius, so it's going to have to be going faster to get all the way around there in the same amount of time.